Happy morning to all. Happy morning. The last class we learned about that the face centered and also the body centered arrangement, that is packing fraction, otherwise called packing efficiency of face centered and also the body centered cubic arrangement. It's a very important question. And about the today we are going to learn about that the imperfection of solid. What is about that imperfection? That means not perfect. Crystal lattice, in crystal lattice, some of the areas are not perfect. Why this happen means missing of cation or missing of anion. Missing, ions are missing. And also the dislocations of ions. The ions are having in the crystal lattice, ions are present in the crystal lattice, ions are occupying the crystal lattice, but it dislocates, it occupies at the interstitial space rather than its own appropriate site. And about metal excess defect. Excess, some of the metals are excess, and about that metal deficient, having some less number of metal, and also impurity of the metals. Okay, anyhow, a very important area, very important area about that stoichiometric defect and about non-stoichiometric defect. Here the point defect can be classified into three types. One is the stoichiometric, another one is the non-stoichiometric, and also one is impurity defect. Here the stoichiometric means they are again classified into two types. One is a short key defect, another one is the fungal defect. Short key. Don't forget that short key means missing of cation and anions. Missing of ions of cations and anions. This is about the short key defect. What is about the fungal defect? Dislocation of ions. Displacement of ions. Fungal defect, the very, the most important question. Short key and fungal. Short key and fungal. The compulsory question. Please all of you take the note, we can be right. We can be draw the diagram also. Diagram also very important. Okay. So, we should be learn this question. Please all of you take the note. We can be right. We can be discuss about that point defect. Point defect. Here the point defect can be classified into three types. Can be classified into three types. One is stoichiometry. Defects. Stoichiometric defects. Non-stoichiometric. Impurity defects. These are the three types. Okay, what is that one? Stoichiometric defect, non-stoichiometric defect, and about impurity defect. Here the stoichiometric defect and again classified into two types. One is about short key defect. Short key defect. Next one is a fungal. The stoichiometric is again classified into two types. One is about the short key defect and another one is called as the fungal defect. Non-stoichiometric defect can be classified into two types. one is metal excess defect. Metal excess defect. Here metal deficiency. Defect. These are the about the point defect. Okay. So what is what? Stoichiometric defect is again classified into two types: short key defect and fungal defect. Here what is about the short key defect? Already I told you about that. Short key defect is a mixing of ion. Some of the ions are missing. It can be say cation and anions are missing from the crystal lattice. Okay, not a cation, but cation and anion, both of them are missing from the crystal lattice. Okay, this is about the short key defect. Examples is NaCl. Okay, that is about the sodium chloride. Very important question. Short key defect is a very important question. About the short key defect, first we draw the diagram. Here one of the negative ions. Next about the positive ions. Next about the negative ions. Negative ion, positive ion. Negative ions, positive ion. Negative ion, positive. Okay. Next here you draw the positive. Okay. Positive, negative. Positive, negative. Positive, negative. Positive, negative. Clear? Next again negative. Negative, positive. Negative, positive. One of the negative, one of the positive is missing. Okay, negative, positive, positive. Here negative. Okay, positive, negative, positive, negative, positive, negative, negative, positive, negative, positive, negative, positive, negative, positive. This is the diagram. Here Na plus, here the Na plus mixing from the crystal lattice. From the crystal lattice, Na plus is mixing. Here Cl minus missing. One of the chloride ion missing. Now what do you understand about this area? What is the concept? Here the missing of equal number of cation and anion from the crystal lattice. That defect is called short key defect. What is about the short key defect? Can you say? It's a very important question. Short key defect. The short key defect arises due to the missing of equal number of cation and anion from the crystal lattice. This is one of the crystal lattice. In the crystal lattice, here the ions are occupying. Am I right? Ions. Chloride ions, sodium ions. Chloride ion, sodium ions. Chloride ion, sodium ions. Chloride ion, sodium ions. Here, sodium ion, chloride ion. Sodium ion, chloride ion. Sodium ion, chloride ion. Sodium ion, chloride ion. Here, chloride ion, sodium ion. Chloride ion, sodium ion. Chloride ion. Here is one of the missing of Na plus sodium ion. Missing of sodium ions. Then chloride ion, sodium ion. Here, sodium ion. Here, chloride ion is missing. Both of them are missing. One of the positive missing and one of the negative missing. Am I right? One of the positive missing, one of the negative missing. One of the anion missing, one of the cations are missing. Here, the number of cation and the number of anions are missing from the crystal lattice. Here, this effect does not change the stoichiometry of the crystal. This is the balanced form. This is a balanced because in the number of positive ions is equal to number of negative ions. It is not only one positive missing. It is not only one negative. Chloride ion is not missing. There is one positive and one negative missing. One cation and one anions are missing. Can you understand? So, this effect does not change the stoichiometry of the crystal. Stoichiometry means balanced. Am I right? Ionic solid in which cation and anions are almost similar size. The size of the cation and the anion are same size, almost similar. Clear? Here the cation and the anion of almost of similar size. Here the very good example is NaCl. What is the example? Example is NaCl. Sodium chloride. So very important question. What do you understand this area? Schottky defect arises due to the missing of equal number of cation and anion from the crystal lattice. This is one of the crystal lattice. Sodium plus ions and chloride minus ions are missing from the crystal lattice. This effect does not change the stoichiometry of the crystal. This effect does not change because here number of positive ions is equal to the number of negative ions. So this effect does not change the stoichiometry of the crystal. The ionic solid is in which the cation and the anion, this cation and the anions are almost similar size. Okay, example. Here, the presence of a large number of Schottky defect in the crystals lowers its density. Don't forget that. It lowers its density. This is the 1 mark question. 1. Okay. What's the 1 mark question about that? Here. The presence of the large number of Schottky defect in the crystal lowers its density. Okay. The example, for example, the thermal density of vanadium monoxide. What is the formula for vanadium monoxide? VO. VO. Okay. The VO means it is a formula for vanadium monoxide. Okay. Anyhow, the calculated edge length of the unit cell is 6.5 GCM inverse minus 3. What's the value? 6.5. 6.5. But the actual experimental density value is 5.6. This is also one value question. 5.6 gram centimeter minus 3. Here, what is about that? The calculated, the theoretical density of vanadium monoxide. The theoretical density of vanadium monoxide is calculated. The edge length of the unit cell is what? 6.5 gram. 6.5 gram centimeter minus cube. Okay, minus 3. Anyhow, but the actual experimental value, what is the experimental value? 5.6 centimeter, 6 gram centimeter, okay, minus 3, okay. Anyhow, it indicates that there is an approximately 14% of Schottky defect in vanadium monoxide crystal, okay. Approximately how much percentage? Approximately 14% of Schottky defect happened in where? Vanadium monoxide. How much percentage? 14%. It's a very important question. Schottky defect. For the 3 mark, some days maybe ask about the 5 mark question. Okay. Next one about the fungal defect. Next one, fungal defect. What is about the fungal defect? Fungal defect means It is about the dislocation, otherwise called displaced ions, dislocation in the crystal lattice, interstitial position rather than its own appropriate site. Okay, they are replacing its own crystal lattice, replaced. For example, we can be taken as silver bromide, AgBr, for fungal defect. It is about that due to the dislocation of ions, dislocation of ions. One of the Ag plus ion is missing from the crystal lattice and it occupies an interstitial position. Clear? One of the Ag plus ion is missing from the crystal lattice point and it is occupying an interstitial position. Okay? Here, Ag ions leaves its normal site. Okay, a small Ag plus ions leaves its normal site and occupies an interstitial position. Okay, that is rather than its own appropriate site. That means this is Br minus ion. Okay, Ag plus ion, Br minus ion, Ag plus ion, Br minus ion. Okay, you can be right. Okay, you can be used only the symbol. Okay, plus minus. Okay, plus minus. Clear? After that, it should be what? Plus minus. Here plus missing. Minus plus. Here what? Ag plus ion missing. Okay? Ag plus. Next here after that minus plus. Minus plus. Okay? Plus minus plus. What of the missing of Ag plus ion? Ag plus ion missing. Minus. Okay. Plus. Here what is happening here? Ag plus in interstitial. Okay. Ag, okay. Ag plus ion in interstitial position. Okay. Here Ag plus is missing. Here missing, but here having one of the Ag plus ion in interstitial position. Okay. Here missing, okay. Here missing, okay. Missing from the crystal lattice, okay. But the ion which is missing from the lattice points and it should be occupy an interstitial position. Okay. That means it is not missing. Actually missing, but it is not missing. We are missing and it should be dislocated. Dislocate from the place. This particular area, in this particular area, Ag plus ions must be present here. But it is dislocate, displaced. We can be say displaced from not its original place. It is slightly moving, slightly moves from its own place. Okay, and it is present on its where in interstitial position rather than its own appropriate site. Okay, its own appropriate site. Okay, now about the Schottky defect means missing of cation and missing of anion. Okay, here about that due to the dislocation. Okay, we can be say it is a correct form. A fungal defect arises due to the dislocation of ions from its crystal lattice. Dislocation or displacement. You can be say like that. Dislocation. Okay. Anyhow, the ions which is missing from the lattice point and occupies an interstitial position. Okay. Here, this defect is shown where ionic solid. Solid, ionic solid, in which cation and anion are differ in size. What is about the Schottky defect? Cations and anions are almost similar in size. Am I right? In Schottky defect, it is almost similar in size. Here about the fungal defect, the cation and anions are differ in size. And about in Schottky defect, what happened here? Schottky defect. The defect about the Schottky defect, the presence of large number of Schottky defect in the crystal lowers its density. But here, this defect does not affect the density of the crystal. Fungal defect. This is a one-word question. One more question. Fungal defect does not affect the density of the crystal. Here, what is the meaning? In AgBr, the small Ag plus ions leave its normal site. This is the normal site. It leaves from the normal site and occupies an interstitial position. Okay, and occupies interstitial position. This area, what do you understand about that Schottky and fungal defect? Can you say? Schottky defect arises where? It is arises from the mixing of one cation and one anion. And about the size is almost similar. What's an example? Sodium chloride. What's an example? Sodium chloride. Sodium and chloride size is almost similar. What is about the fungal defect? It is due to the dislocation of ions from its crystal lattice. It arises due to the dislocation of ions from its crystal lattice. Here, what is about the size? The size of cation and anions are differ in size. It does not affect the density of the crystal. It does not affect the density of the crystal. What is about the next point? Ag plus ions leaves its normal site and occupies at an interstitial position. These are about what? About the fungal defect. Next about metal excess defect. This is also a very important question. What is about the metal excess defect? Here we can be saying the example is sodium chloride. When the sodium chloride crystals are heating in the presence of sodium vapor. Okay, sodium vapor. Na ions are formed and deposited on the surface of the crystal. Here, Na plus ions is an excess. Am I right? Na plus ions, here excess. And it is the color is about the brown color. Am I right? Brown color is, which shows the brown color excess. So we are saying excess, metal excess. Sodium is excess. We can be saying metal excess defect. Okay, metal excess can. That is, metal excess defect arises to the presence of more number of metal. Clear? It is not a stoichiometric. It is a non-stoichiometric form. Schottky and fungal defects are stoichiometric. Okay, Schottky and Fendel defects are stoichiometric defect, and about the metal excess defect and metal deficient defect are the non-stoichiometric. Okay, non-stoichiometric form. Okay, anyhow, here the metal excess defect arises to the presence of more number of metal ions in as compared to the anion. Okay, first we can draw the diagram. This is the chloride ions. Okay, next one is the sodium ion. Okay, sodium, chloride ion. Okay, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion, sodium ion. Okay, next one, sodium ion, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion. Next one, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion, sodium ion. Here one of the chloride ion is here, unpaired electron. Here is an unpaired electron, E minus. Okay, unpaired electron. We are saying that one F center. Is we say F center. F center. Okay, that means we are saying unpaired electron. Unpaired electron. Okay, then sodium ion. Sodium ion, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion, sodium ion, chloride ion. Okay, anyhow, here we can be take as alkali metal halide. Alkali metal halide, NaCl, KCl. And these are the examples we can say as a metal excess defect. The electrical neutrality of the crystal can be measured by the presence of anionic vacancy. This is the anionic vacancy. Am I right? Anionic vacancy is equal to the excess metal ion. By the presence, otherwise we can be say by the presence of extra cation and electron present in interstitial position. How can we give the example means? For an example is NaCl crystal. The sodium chloride crystals are heated in the presence of sodium vapor. Am I right? That is an equal balance in NaCl. When heated in the presence of sodium vapor, here Na plus ions are forming. These Na plus ions are increasingly forming. And these Na plus ions are deposited on the surface of the crystal. But in the case of sodium, in the case of chloride ions, diffuse to the surface from the electric points and combines with Na plus ion. Here what is happening is, the electron lost by the sodium vapor diffuse into the crystal lattice and occupies a vacancy, one of the vacancy, and occupies a vacancy created by the Cl minus ion. Such anionic vacancy, that means we can say the negative charge, such negative charge vacancies which are occupied by unpaired electrons, these unpaired electrons are called as F senders. Which senders? F senders. Okay, here The sodium chloride contains excess Na plus ions and can be written as, this sodium chloride can be written as per the formula, Na1 plus X Cl. This is the formula. Na1 plus X Cl. Here, the examples of sodium chloride crystal. The sodium chloride crystals are heated in the presence of sodium vapor. Na plus ions are formed. Here the Na plus ions are deposited on the surface of the crystal. What happened? The chloride ions diffuse to the surface from the lactic points and combines with Na plus ions. The electron lost by the sodium vapor diffused into the crystal lattice, and occupies a vacancy created. Am I right? A vacancy created by Cl minus ion. Such anionic vacancy, one of the anionic vacancy means negative charge. Anionic vacancy which are occupied by unpaired electron, that is called as F centers. That is called as what? F centers. Okay. Next about, we can say one more example. What's an example? Is zinc oxide. What is the color of the zinc oxide? Zinc oxide is a colorless at room temperature. What is the formula for zinc oxide? ZNO. It is a colorless at the room temperature. When it is heated, it becomes yellow in color. Okay? Zinc oxide is colorless. Am I right? Zinc ZNO is colorless. When the zinc oxide is heated, it becomes yellow color. When the zinc oxide is heated, it becomes yellow color. On heating, what happens? It loses its oxygen. Zinc oxide loses its oxygen, and thereby forming free Zn2 plus ion. Zn2 plus ion. The excess Zn2 plus ion moves to the interstitial site, and the electron also occupy the interstitial position. This is another example. Okay. Here the excess Zn2 plus ions moves to the interstitial site, and the electron also occupy the interstitial position. Okay. Next about the metal excess defect. Okay. Metal deficient defect. Here deficient means some shortage. We are saying some less number of cation and anion. Okay. Less number of cation than the anion. Metal deficiency defect. Metal deficiency defect. Here, metal deficiency means some shortage, some less number of cation than the anion. Okay. Here we can draw the diagram. This is the O2 minus 1. Okay. Next one is, we can be taken as Fe2 plus. Next again, O2 minus 1. Fe3 plus. O2 minus 1. Fe2 plus 1. O2 minus 1. Okay. Fe2 plus 1. O2 minus 1. Fe2 plus 1. O2 minus ion, Fe2 plus ion, O2 minus ion, Fe2 plus ion, O2 minus ion, here Fe3 plus ion, okay, Fe3 plus ion. Next again, O2 plus ion. Here have some vacancy. Some of the vacancy, some of the deficiency, we can be saying some deficiency. Some deficiency, okay, O2 minus ion, O2 minus ion, Fe2 plus ion, again having Fe3 plus ion, Fe3 plus, okay. O2 minus ion, sorry, Fe2 plus ion, O2 minus ion, Fe2 plus ion, O2 minus ion, Fe2 plus ion, O2 minus ion, okay, O2 minus ion, Fe2 plus ion. Here we can say Fe3 plus ion. Here, yeah. What is about the metal yet deficiency? Having less number. Metal deficiency means having less number of cation than the anion. Metal deficiency arises due to the presence of less number of cation than the anion. Here, this defect is observed in the crystal, which is cation have variable oxidation state. Don't forget that cation have variable oxidation state. Cation have variable oxidation state. Okay, cation having variable oxidation state. For example, FeO crystal, this is about the FeO crystal. Some of the Fe2 plus ions are missing from the crystal lattice. Okay, some of the Fe2 plus ions are missing from the crystal lattice. Here we should be maintain the electrical neutrality. To maintain the electrical neutrality, twice number of other Fe2 plus ions in the crystal is oxidized to Fe3 plus ion. Clear? What is that? To maintain the electrical neutrality, twice number of other Fe2 plus ion is oxidized to Fe3 plus ion. In such a case, the overall number of Fe2 plus ion and Fe3 plus ions is less than O2 minus ion. Less than O2 minus ion. Clear? What is about this point? Here, such is happened. To maintain the electrical neutrality, twice number of Fe2 plus ions in the crystal is oxidized to Fe3 plus ion. Clear? Fe2 plus ion is oxidized to Fe3 plus ion. Anyhow, overall number of Fe2 plus ion and Fe3 plus ions is less than O2 minus ion. Okay. So the experimental found the general formula of ferrous oxide is Fe2O3. Am I right? Fe2O3. This is the general formula. And X ranges from 0.93 to 0.98. This X ranges. That means FEX. We can say FEX. Okay. X. Here X ranges from 0.93 to 0.98. Ranges from 0.93 to 0.98. Okay. This is also very important for the one word. Next about that. Next one, the last area is impurity defect. Impurity defect. What is about the impurity? Here, the impurity ions are different valency state from the host. One of the host. Clear? The impurity ions are different valency state, not same valency state. Different valency state from that of host. Vacancies are created the crystal lattice from the host. For example, cadmium chloride CdCl2, cadmium chloride. Cadmium chloride to silver chloride. Here, the addition of cadmium chloride, to silver chloride, we get its solid solution. Which is solution? Solid solution. Here, the addition of cadmium chloride to silver chloride is a solid solution. We get there where the divalent of Cd2 plus Cd cadmium 2 plus ion occupies the position of Ag plus ion. Thus, there will be a distribution of electrical neutrality of the crystal. So, in order to maintain the same proportional number of Ag plus ion leaves the lattice. Okay. In order to maintain the same proportional number of Ag plus ion leaves the lattice. This produces a sudden vacancy in the lattice. Some of the vacancy. So it is happened. It creates some vacancy, cationic vacancy in the lattice. Such a kind of crystal lattice are called as impurity defect. Okay. Impurity defect. Anyhow, today our assignment. Today we learn about the short key. Don't forget that short key defect, Frenkel defect. Very, very important. So assignment topic. Short key defect. Short key defect and Frenkel defect. Okay. Thank you all of you. Thank you. Have a nice day.